So let's talk about gas chromatography. So it's a technique for separating and analyzing compounds that can be vaporized without decomposition. So I think the maximum operating temperature for a normal GC is up to 300 degrees Celsius. So if your sample do not decompose at high temperatures, then GC is the way to go. So here's a schematic of GC. From the name itself, our mobile phase is an inert gas, normally helium, and then the helium gets filtered before it gets introduced into the GC system or into the column. And then you have an auto sampler, or you can actually manually inject your sample into the injection port where it meets the carrier gas. So the sample and the mobile phase travels through the column, which is temperature controlled, and then the analyte gets detected. So just like what I said on the introduction for GC, the analytes are separated based on their strength of interaction with the column. So the column is usually a fused silica or a metal tube where you have a stationary phase coated on the inside walls. So those that have weakest interaction with the stationary phase in your GC column will get eluted first, will get detected first. And the one with the strongest will get eluted last. So the time of elution is sometimes referred to as the retention time, and you will see that on a chromatogram, a typical chromatogram. So common detectors for GC are flame ionization detector, mass spectrometer, which we talked about earlier, thermal conductivity detector, and electron capture detector. So for GCFID, or flame ionization detector, the detector converts your analyte into carbon ions. So how does it do that? You ignite the detector, so you introduce the flame, and then you introduce hydrogen gas to form those carbon ions. And the carbon ions formed are detected by a cathode collector. So on the other hand, GCMS, we already talked about this, but same concept. The analytes that are being measured get introduced to a mass spec, and the analyte gets converted into ions, normally using electron ionization methods, and then the mass or the ions are sorted out using a mass filter and then gets detected. So here's a typical chromatogram generated by a GC. You see, like I said, you have a retention time on the x-axis, and then it's plotted against abundance of your analyte. And like your UV-Vis spectroscopic techniques, you need a calibration curve to quantify the analytes in a GC analysis, and sometimes you also use what's called an internal standard. So applications, here's a short list of applications for GC technique. So you can use it for environmental analysis, like analysis of greenhouse gases like carbon dioxide, methane, and NOx in air, pesticides, and trihalomethanes in drinking water. You can also use it for clinical analysis, such as in drugs and blood alcohol analysis, forensics, consumer products, and petroleum and chemical industry. And you can also use it for pharmaceutical products, where normally you want to measure the residual solvent of your manufactured drug substance.